Problem 65 states that a typical laboratory centrifuge rotates at 4,000 revolutions per minute. Test tubes have to be placed into a centrifuge very carefully because of the very large accelerations. Part A wants to know what is the acceleration at the end of a test tube that is 10 centimeters from the axis of rotation. So here I've drawn our centrifuge, our axis of rotation. Test tube is going to be 10 centimeters away from that axis of rotation. And we've got our tangential acceleration, which runs tangent to the center of the circle, and we have our centripetal acceleration, which runs towards the center of the circle. And we need to figure out both of those before we can figure out our magnitude of acceleration. So we know we're rotating at 4,000 rotations per minute, and we want to convert that into radians per second in order to find our angular velocity. So just times revolutions per minute times 2 pi radians per 1 revolution, 1 minute per 60 seconds, and we get our angular acceleration, our angular velocity at 417.83 radians per second. So we can use that to find our centripetal acceleration by using this equation here. So just the angular velocity squared times the radius. So we can plug in those numbers. Radius of 0.1 meters, which I converted from 10 centimeters. And we're left with 17,458 meters per second squared. Now, in order to find our tangential acceleration, we need to find our angular acceleration and times it by our radius. So, find our angular acceleration, we just divide the angular velocity by the time. So, the time we can find how many seconds takes to do 1 revolution. We can use this equation here, and we find that 0.015 seconds is how long it takes to do 1 revolution. So we plug that in for t, plug in our angular velocity, and we get 27,785.57 radians per second squared for that angular acceleration. Now we can plug that back into our tangential acceleration equation, and we find that our tangential acceleration is 2,778.56 radians per second squared. And now, to find our magnitude of acceleration, we just take the square root of that radial acceleration, or centripetal acceleration, plus our tangential acceleration squared. Plug those numbers in, and our final magnitude of acceleration is 17,677.7 meters per second squared. So for part B, for comparison, what is the magnitude of the acceleration a test tube would experience if dropped from a height of 1.0 meters and stopped in a 1.0 millisecond long encounter with a hard floor? So this wants to know what the magnitude of acceleration is if that test tube were to fall. We know the height is 1.0 meters. We know the time it takes is 1.0 meters or milliseconds, which we can convert to seconds, 0.001 seconds. And we can just use this simple acceleration equation. To find our velocity, we want to use the equation for falling objects, which is just velocity squared equals 2 times gravitational force times the height. Plug in our numbers there, 9.81 for gravitational force, 1.0 meters for the height. Divide that by our 0.001 seconds, and we have 4,429.4 meters per second squared is the magnitude of acceleration that test tube is going to experience when we drop it from that height. And the context of this question helps us to identify acceleration vector for curvilinear motion and also to understand angular acceleration and the kinematics of non-uniform circular motion.